Okay, great stuff. So yes, this session, I'm going to talk about emerging web app architectures using Java and Node.js. So myself, I work for IBM, as has just been mentioned, as part of their runtime development team. And I started working on IBM's versions of Java in around about 2000. So I've been doing Java for something like 16 years. But in the last couple of years, I've also started working with the open source communities for Node.js, and over the last 12 months or so for Swift. So I've actually been working on the language runtimes for Java, Node, and Swift recently. And through working across multiple languages, we're starting to see that real enterprise customers are no longer making a single language choice. They're starting to build these polyglot deployments where small teams, as you start to build out microservices, are choosing a language for the task that they're trying to do, more than just saying, what's the choice for our enterprise? What is it what we standardize on language-wise? So that's what I'm going to talk about in this session. Now, one of the things I said was, I've been working on Java since 2000, which was back in the days of Java 1.1.8. And probably every year that I've been working on Java, there's always been some kind of Java is dead message going around, whether it was been on Slashdot or whether it's been published on a various forum or through an article. So this is one that was taken from Java World last year with their prediction of developer trends in 2016. So they said, trend number 2, Java is declining and the language decline will continue to accelerate. And they're basing this on a number of things, but in particular, they were looking at jobs because usually when someone says Java is dead, everyone says, yeah, but actually there's quite a lot of jobs, and there's been a 5% increase in the number of Java jobs over the last 12 months or so. But Java World was saying that, yeah, but those are maintenance jobs. The cool development jobs, which is new investment, is all around Node.js, Spark, MongoDB. So we get this perennial thing where it says that Java is dead. Now, some of that is driven from things like GitHub. If you look at the GitHub statistics, since around 2013, JavaScript has been the most used language for GitHub projects, and Java is second. Now, the interesting thing is that Java's actually risen to second. It's not like it was ever in first position. And to a certain extent, that's not surprising. Statistics can be read whichever way you like. One of the key things is that JavaScript is a scripting language, right? There is no compiled version of it. I can't give you a binary and ask you to use that. I have to give you my source code. So it kind of inherently fits open source projects. But this is one of the things that people point to say that, Java is not the #1 language anymore, and things like JavaScript are. So in GitHub, JavaScript is the most used open source language, and Java comes in second. Another example that's given is around the availability of packages. So NPM, the Node package manager that's used for Node.js JavaScript, not only has the largest number of packages available, it's something like 335,000 packages today, it's also the fastest growing. And as it turns out, Maven and Maven Central is actually the #2 package provider. But at #2, it has less than half of what NPM does. So again, people kind of say that this puts Java behind where JavaScript and NPM is, and it's not even growing at the same kind of rate. Now, of course, one of the things to say is that in JavaScript and Node.js terms, everybody uses Node Package Manager. That's where every single package is. There are no other delivery routes that people use, whereas for Java, it's still common to go to apache.org or individual projects or to Eclipse to get those projects. So it's kind of not measuring apples to apples, and maybe that's some of the reason. But one of the other things that's been kind of affecting Java, and I'm sure we're all aware of this, is around vulnerabilities in the browser. So we have the statements from Homeland Security and US CERT, both pretty much saying, if you still have Java in the browser, you should disable it and you should remove it. And since then, Oracle's done what I think we would largely agree is the right thing and removed support for applets in general. But this has led to the situation where these are the current statistics for language usage in the browser client. And it basically says that JavaScript is the only thing that people are using for client-side programming in the browser. Java with the plugin used to be represented on this slide, but they removed it once it went under 0.1%. So basically it's, JavaScript is one in the browser. So why has there been this growth of usage of JavaScript and Node.js, the server-side implementation of JavaScript that allows you to get outside of the browser sandbox and interact with the operating system and do real server workloads? Why has JavaScript and Node.js become so popular over the last 5 years? Well, part of that is around rich web applications. We know that back when Tim Berners-Lee came up with the concepts of the World Wide Web, we had static pages with static content that linked from one page to another, and that was it. And we've now moved to the point that we're doing rich web applications to the point that Google Hangouts is running in the browser. You have full word processors and spreadsheets available for you to run in the browser. And this is giving us very, very rich web applications that are written in JavaScript. And because they're written in JavaScript, you start to get this benefit of being able to do server-side JavaScript as well as client-side JavaScript, what's called isomorphic development. So this is like another version of write once, run anywhere, which was that key goal back in the day for Java, being able to run on every platform. But this is now talking about being able to run in the client or on the server. In fact, ideally, both, because then you get to share the data model between the client and the server, and there's less maintenance, and there's less chance of having defects cropping up because you've changed the data model on the server and you've changed it on the client, but you've not managed to keep them in sync, or the change has been subtly different because of typing or the like. And the other key difference that's started to push for JavaScript inside the server, serving up JavaScript for use in the browser, is around server-side rendering. So one of the challenges with these rich web applications is that when you deploy your application to the browser can't actually start running the application until it has all of your code. So there's a delay before it can start rendering the page. Now, one of the things you can do when you can run the JavaScript on the server is that you can actually pre-render the first instance of the page and deploy the rendered version to the browser, and then send the JavaScript to allow it to dynamically update afterwards. And this actually gives significantly better first paint time for the browser application. And the other advantages of it is that not all search engines and search engines in general aren't very good at doing indexing based on the contents of dynamic JavaScript. So by being able to do a pre-rendered version which deploys down to the browser, it's much easier for the search engine to index the sort of content that's on that page at runtime. So it's a whole number of things that have started this process where development using JavaScript for rich browser applications is starting to leach over to the server. Very much like happened for Java in the very early days when, Java, when it was called Oak before it became Java, was designed for set-top boxes. And some of its very first demos were as UIs designed for use in the browser, and then server came next. And that's kind of where JavaScript has been going for the last 5 years, starting off as rich web applications. And now people are seeing some advantages of running in the server around this isomorphic development and being able to do server-side rendering. Now, another of its big advantages for people who are JavaScript developers in the browser is how easy it is for them to get started with their first application. So in order to write a simple hello world-based HTTP web server, you actually only need the 8 lines of code on the screen. So you do var HTTP equals require HTTP, so that's an import statement. HTTP.create server, so create your server. It then has first-class function callbacks. So you're registering a callback for the request response, and you're telling it to send back hello world and asking it to listen port 8080. And that's it. 8 lines of code gives me a hello world response on a server. And in fact, if you then want to cluster it, certainly on the same machine, clustering is really easy as well because that's built into the language. So you import the cluster package, you import the OS package to find out how many CPUs there are, and for each CPU, you fork an instance of your application. And under the covers, it automatically shares port 8080 when it does that. So any listener port that you've got is going to become shared across all of your worker instances, and it load balances on a round-robin basis. So in 8 lines of code, you had a simple web server. In another 12 lines of code, you've been able to do clustering across the machine, and you've pretty much built a resilient, simple hello world server that's actually capable of replacing instances if they fail, because they have a death event that you can register for. And one of the things you can do inside death, if you wanted to, is called cluster.fork to create a new instance if one of the child processes disappears. And it's that kind of event-based programming that's made it kind of popular and kind of scalable. Because not only can you create that server, there's no sense of threading. So you don't need to have a thread pool that contains your ability to handle incoming connections. You're not limited to 50 concurrent connections because you have 50 threads in your web container pool. It uses asynchronous non-blocking I/O, the sorts of things that have now been added to Java and available through frameworks like Netty, but it's there out of the box, and it's always been that way. So in some ways, Java has started to do catch up by including lambdas so that you can have callbacks on events, and having async non-blocking frameworks like Netty to allow you to do what you can actually do in Node.js, and you have been able to since day one. So if that's why people are using JavaScript and Node.js, then why are people still using Java? And probably the first and the most obvious reason is performance. And we all know, as people who've built and deployed enterprise Java applications, that the performance is very good. You know, we had a number of years back in the day when people would say that, you know, but the performance of Java is very, very poor. But that simply isn't true anymore, particularly with the quality of just-in-time compilation that we have, and the ability to do runtime recompile to decide, you know, how to order a switch statement according to which are the most common paths through that switch statement. And that's something that other languages just can't do. And that's certainly the case for Java versus Node.js and JavaScript. So the numbers here are taken from the benchmarks game, which is a set of computational algorithmic benchmarks. So it does what our American colleagues would call math, what we in England would call mathematics or maths. And it does simple calculations repeatedly over multiple cores. And they run these benchmarks and basically see how long they take to complete the mathematical task. Now, in every case, and remember that lower is better, blue, which is JavaScript, is faster. Blue, which is Java, is faster than green, which is JavaScript. So Java massively outdoes JavaScript for computational tasks across the board, and anywhere between like 4 times and 10 or 15 times faster. And that's computational workloads. Now, what about web application workloads? Because we're talking about web apps here. Well, there's another group. This one's called Tech Empower, and they do a similar thing to the benchmarks game. They actually run the benchmarks themselves. They don't rely on people to submit benchmarks like happens with SpecJBB and SpecJ App Server. You provide them with an instance, so you provide the code, and they run the test on the same hardware, and they do it for a large number of different programming languages and a large number of different frameworks. And what's compared here is the performance of Node.js versus Java. And in fact, the best Java framework in general is a Netty-based framework. So what we see for JSON serialization, and what this does is it receives a request on a URL, and it literally just returns hello world in a JSON object. Now here, higher is better. So blue, which is Java, runs at 100, and that's actually 100%. So we've got marked 100% as the one that's fastest, and the other one is a percentage of that. So JavaScript runs at about 10% of the speed of Java in this case. So it's 10x slower than Java at returning a JSON object containing hello world. And one of the things that you might consider to be quite interesting about that is that JSON is JavaScript's object notation. So you would have thought JavaScript is going to be really good at returning JSON. But basically what it comes down to is when you're just returning a JSON object, it's actually quite a lot of computation. And this is a CPU-bound benchmark, right? That your instance will run at 100% CPU, and it does for JavaScript and it does for Java. And as a result, JavaScript runs 10x slower. Now, the second benchmark they do is a single query. So it's much the same thing. There's an incoming request that goes to the web server that's being tested, which then reaches out to a backend database, gets a result from that, then creates a JSON serialized version of it and returns it. So pretty much it's an extra step that goes out to the database to do a query. And when we run this, we find that Java is still much faster than JavaScript, but only 2x faster. And this is because JavaScript's actually really good at I/O. But there's actually only one step of I/O here, but it's significantly slower at computational tasks. So that's why it's still behind. Then what we do is we move to a third benchmark, which is data updates. Now, what this does is more of a CRUD style operation. So it gets an incoming request, it goes to the database, it does a read, does a manipulation, does a write back, and then sends the result to the incoming request. And when we do this, we actually find that JavaScript is slightly faster than Java. And it's only about 10 or 15%. But basically, there's a trend, and we see it for more complicated benchmarks as well, that as you get more and more I/O and the application becomes I/O bound, JavaScript actually starts to outdo Java. And that's including using high performance concurrent I/O frameworks like Netty. But at the other end of the scale, anything that really burns CPU and does computational workloads is significantly faster in Java. And one of the reasons for that, the reason Java is significantly faster isn't because Java has a just-in-time compiler and JavaScript doesn't, because JavaScript has the V8 compiler, which has, the V8 runtime, which has a compiler inside it. So it has a just-in-time compiler. It's all to do with typing. And you'll actually see that in the next set of slides. So one of the big advantages for Java, as well as being faster at computational workloads, is type safety. So on the left-hand side here is hopefully what you'll recognize as some Java code. And the equivalent JavaScript code is on the right-hand side. So in both cases, it's taking two variables and it's going to use the plus operator on them. So on the left-hand side, we have add int int. On the right-hand side, we have add and the function AB. Now, in JavaScript, we don't have typing, so it's not ints, they're just two parameters. Every parameter is a var. So if I then pass in the values of 5 and 3 and ask it to add the two, on Java, we have to do a compile, so we run javac. On JavaScript, because it's scripted and there's no binary form, we don't have to do that. And then we run it. Now, what we get in both cases is exactly what we expect, which is the value 8, which is the sum of 5 and 3. So the plus operator has been a sum, and that's what we expect. Now, what happened there? Now, what happens if we change the values of 5 and 3 to being a string for 5 and still the number 3. Now, what happens if we do this in Java and we run the Java-C compiler is that we immediately get an incompatible type error. So the fact that I've tried to say I want to add 5 and 3 together and one of them isn't a number means it immediately tells me there's a problem. Now, on JavaScript, there isn't a compile stage, so you go straight to the run stage, you run it, and you get a result of 53. And this is one of the problems with JavaScript. So that plus operator will execute regardless of what your intent was. You may have intended only for the add function to accept numbers. So you may have intended to have the result of 8 because you thought 5 was a number and you thought 3 was a number. But if you use one of those parameters at any point as a string, then it will actually concatenate the two and give you 53 rather than 8, which is kind of a problem if you're doing financial calculations when you've accidentally had a result that's 45 larger than you might expect. And this is a particular problem if you're using JSON REST APIs, because JSON isn't typed. So when it comes in, I'm really just receiving strings over the wire. So it's quite easy for me to accidentally interpret something as a string when I expected it to be a number. There's actually a number of strange things like this for JavaScript. So here's what we've just shown you, that 5 plus 3, if they're both numbers, gives you 8, and 5 plus 3, if one of them is a string, gives you 53. Now, you can actually minus a number from a string. So if you take the string 5 and you minus 3 from it, you get 2 back. And that's kind of possibly what you would expect. It's taken 5 and it's actually converted it to a number, and then it's minus 3 from it, and we got 2. Now, you can actually minus one string from another. And if you minus 2 strings, you get 1 because it implicitly converts them to numbers. And that's might be what we expect. Now, another strange one is if you have 2 pluses, it doesn't give you an error, which you would get in Java. It actually just processes it. And you end up with 54. So it does a concatenation. Now, if you did hello plus world, you got hello world. I think that's what we would all expect as well. Now, here's a strange one. If we have hello, have the 2 pluses, which was acceptable to do before, and world, what you end up with is hello, not a number. And that's because when you've got 2 pluses, it tries to convert them to numbers. It tries to convert the second one to a number, and it says world isn't a number, but it still doesn't give me an error. It just processes it. So we've got this challenge with JavaScript that it may be fast to develop and it may have a rich ecosystem of packages, but it's very slow at computational tasks. And that lack of type safety means that, one, I can't guarantee how things are going to run. I don't have the guarantees that I'll spot my errors at compile time. And this is actually why computational tasks run slowly, because in Java, if I add 2 ints together, I know that they're ints, and that's a single instruction. That's an add-I. In JavaScript, and I try to add 2 variables together, the first thing JavaScript has to do is try to understand what those 2 variables are. Is one a number? Is one a string? In fact, you can add 2 objects together in JavaScript, and you can add a function to an object, and all of these things are allowed. So it has to be able to check which of the many bits of behavior it needs to execute based on the types of the variables. And that's one of the reasons why Java is so much faster than JavaScript for computational tasks. So language selection. Okay, so we've said that there's a rich ecosystem of packages and there's lots of people using JavaScript. And one of the interesting things is for those benchmarks with the performance benchmark game. One of the things the performance benchmark game does is they actually show you how much code is required to write the implementation of the benchmark. And you actually need something like half the code to implement the same benchmark that you do in Java. So you can actually write things faster, mainly because you don't have to worry about types. Everything is var, and that makes it much easier to write the code. It then obviously introduces problems later. We have this thing that JavaScript is much slower, though, for computational tasks. So if you're doing anything computational, having a 4 or 5x multiplier for using Java is something you can't ignore. And you've got the things around type safety. That means you'll find your errors quickly and you won't misprocess financial calculations if you're using Java. So we seem to have this model where I/O is fast in JavaScript, it's fast to develop, and there's a rich ecosystem of packages, and it produces highly scalable I/O. But Java gives us type safety and consistency and error checking and very fast computation. So this brings us to the concept of microservices. Now, and we're really seeing this with a large number of enterprises, as people are starting to decompose what was monolith applications, or they're starting to do new development, and they're following this microservices paradigm of do one thing and do it well for each instance, then you can actually create small targeted microservices that are targeted to their task. And you can have them self-contained and really designed to be good at what they need to do. So that starts to say, if you're doing business logic, then Java is the language you should be using. If you're building a front-end web tier, which is going to interact with a browser-based application, and you want the advantages of client-side rich applications with server-side rendering and sharing of code between the browser and the server and highly scalable I/O, then Node.js is the right answer. And as I said, this is what we're starting to really see customers do. So Node gives you that high performance I/O and full stack development, and Java gives you the processing performance, type safety, and you've got transactional processing frameworks. But together, you get these highly scalable, 4-tier or microservices architectures that give you rich browser applications and web scale very, very easily. So some of those emerging architectures. So everyone's aware of the old school 3-tier architecture that anyone that's done Java for a handful of years would have implemented at some point, with a large application server tier that kind of did everything. It served up the application through servlets or JSPs. It provided the business logic through the likes of EJBs and did the database connection through JDBC drivers. So what we're now starting to see is that we have people who have their client running in the browser, doing usual HTTP and HTTPS connections to a load balancer with Java instances, and they were connecting to a backend database and wrapping it with operations and management. And that's what people were doing. Now, to start to move to this concept of 4-tier architectures with Node.js, what's starting to happen is that same business logic is being moved slightly to the right and still continuing to do what it did today. But there's the introduction of a new rich application tier in Node.js that's responsible for serving up the application experience to the user. So it's not doing the business logic, it's just dealing the front end pane of glass to the user. And then obviously having another layer of load balancing to talk to the back end, where generally the use of JSPs and servlets has been removed, and something like JAX-RS is being used to provide a REST API. So that's the first stage of introducing a new JavaScript front end. And that starts to look like the 4-tier architecture that Forrester's talked about, where you have a client tier, which is the user's device. You have a delivery tier, which is where you've created an application-specific experience. An aggregation tier, where you may be pulling data for more than one service, doing filtering or the like to provide some REST APIs for use by the delivery tier, and those backend services themselves, whether they're existing databases or whether you're using things like Twitter or OAuth or whatever. So that means you've already kind of moved towards that architecture by adding in a presentation tier as the delivery tier. But when you start to scale this across the enterprise and you have a sense of reusable services rather than ones dedicated to your application, then we can start to look at, well, what other services do we need? Do we want some JavaScript-based services? And moving those services to a back-end common tier used by every application. using things like databases and other things like Twitter and Watson and OAuth, etc., for less database-based services, but things provided by third parties. And then inside between your presentation tier, which is very application specific, and these common services, you start to add an integration tier. And IBM's doing this with a product called API Connect, but there's other API gateways out there like Apigee and a number of others. And what these are doing is they're starting to provide you some governance around the services, but also the ability to aggregate 2 or 3 services together and do filtering and the like at that level. And now what I'm going to do is I'm going to pass over to Josh from PubNub, who has actually built a kind of a demo application that shows this concept of using Node.js and Java in the right place for the thing that you're trying to do. And he's built a serverless chatbot that uses some IBM Watson services along with using PubNub blocks. So I'll hand over to Josh.
Thanks, Chris. Let me get my screen share working here. All right. Hopefully everybody can see my screen now. I created a chatbot called Mr. ROCKBOT. And in fact, let me switch over to the live demo. So Mr. ROCKBOT, I can say, tell me a joke. And he will come back with a really bad joke. What did geologists call a benzene ring with iron atoms replacing the carbon atoms? A Ferris wheel. Let's ask him another one. But he can also tell us useful things like, what is quartz? And it's pulling out some information from Wikipedia, including an image and a link. And he also has translation ability, so I can say, tell me a joke in French. And it figures out that this is French, it converts it to English, finds a joke, and then converts the joke back to French. Hopefully this is still as funny in French. Perhaps it is not. So that is Mr. ROCKBOT. And to put it together, so chatbots are interesting because they need low latency and natural language processing. It has to understand, it has to break apart the sentence or sequence of sentences into something that the computer can understand. Typically, it's also going to need translation because not everyone speaks English, though many of the services which we're going to use are English only. It needs to handle text, images, and links. And the best way to do this is to combine lots of microservices. And so we went with a serverless architecture in the sense that I have not set up my own web server other than to host the static HTML. I don't have to administer my own server. I don't have to host anything. I don't own anything. I want to run my code at a higher level, the level of a module or an object or even a single function. And there are many serverless providers out there, and one of the advantages is that I can pay by usage, not by installed infrastructure. And it lets me leverage microservices, either ones that I've created or that are provided by third parties, as Chris said. And when you hear the word serverless, people either think, well, that's ridiculous. There's still servers. Yes, there's still servers, but you don't have to administer them. And the other thing is, say, well, I've got all this code. I can't move it to someone else's server, someone else's system. Well, generally, serverless applications aren't truly serverless. It's a hybrid. There are some things that you keep running on your own servers and some things that you can outsource or host on third-party systems. So for this chatbot, first thing I did was create a knowledge base. And so my knowledge base, which contains a lot of the computational work, is a Java servlet. And it starts with this big JavaScript, this big JSON database of information, which I created, which comes from Wikipedia and a bunch of geology jokes that I found and some just other interesting information that's geology related. Once I had that, I could put together my application. Let me switch here. So this is the application architecture. Now over on the side, we see the client, which could be a web page or a mobile application or Facebook chat or whatever it is. That goes into some sort of a network which is going to handle these messages. Once in the network, it's going to call out to our services. So the first thing is we need natural language processing. So this is where I used Watson's AI services. They have a ton of really interesting services for NLP, where it can analyze the text, pull out the verbs and the subjects and nouns. Text to speech, so it can convert text into audio waveforms or vice versa, and also translation, where it can convert between 20 or 30 something languages. And it has, the API is fundamentally REST-based. It is a microservice, so they have libraries for Node and Java. But at the end of the day, it is a service running somewhere else that we are calling from this network chunk here in the middle. So Watson is handling the natural language processing. As part of this, it detects the language. If it decides that the language is not English, then it's going to send it to a translation step using another Watson service. When that comes back, it sends it back here to natural language processing to pull out the subjects and verbs. Once it's done that, it's going to go to find, it sends that down to the knowledge servlet. When that is returned, it will go through another translation step if necessary to convert back to the client's original language. And then it sends it back out through the network, which could go to the original client, like we were doing here, or if you were in a group chat setting, then it would send it to the other clients. Now, the knowledge servlet is a Java servlet, and it's hosted on Bluemix. So again, I didn't have to run my own infrastructure. And it's not like an Amazon instance or a Linode where it's not my own physical server, but I still think of it as a server and install Ubuntu and stuff. With Bluemix, I just created a servlet directly in NetBeans and produced a WAR file and put the command line, install it into my Bluemix account and say start. I don't have to provision anything. I don't have to think about how many concurrent instances there are, load balancing, any of that, not even IP addressing. They just give me a URL and I can start to talk to it. Now, finally, what connects all of these things together? Now, you could run your own server to handle all of this coordination, but there's a better way to do it, which is using a data stream network, like what we have at PubNub called PubNub Blocks. PubNub Blocks is where you can put your computation into the network. Essentially, your message comes from the client. It's automatically routed through our network to one of 15 data centers around the world. And you have some code that runs in our network and coordinates all of these different services to produce the final answer and then sends it back out to the client. Now this, as you might expect, doesn't do much real work. It's a simple bit of logic, very little computation. It's coordinating all of these other things. So it's I/O heavy, whereas natural language processing and translation and the knowledge base are all CPU heavy. So that this I/O heavy work is actually Node.js code. You're writing simple JavaScript with promises. And I'll give you an example of what this looks like. So this is very similar to what you would do in a web page. It's an XML HTTP request where you're fetching to a URL with some HTTP options. Then this is the new promise form of callbacks common in JavaScript. So when this returns, this function right here will be called with the value X. And then we're going to publish on an output channel a new message where we say the account was the chatbot because it came from the chatbot, and the text of the message is x.body. So this is what I did to get the final response. Very simple, and it's very I/O heavy. So what we learned from this is that you want to use Java for CPU-intensive tasks, Node.js for I/O-intensive tasks. Definitely use external web services for domain-specific tasks. So for natural language processing, I'm not an AI expert. I'm a UI guy. I don't need to learn how to do all this stuff. IBM has tons of PhDs who can handle that for me. So I call out to their service. And then use asynchronous JavaScript for coordination, which is what we have in PubNub Blocks. Now to get started, I'm going to be publishing a blog on all of this, including the source code to everything. So to get started, at IBM.com, you can get a Bluemix account, a 30-day free trial, and the Watson services you activate within Bluemix. Even if you're not hosting code on Bluemix, you set them up there, and then you can call them from whatever. At pubnub.com, you can get a free account, which will give you 1 million messages a month. And the blocks part, where you put computation into the network, is currently free, and our final paid and free tiers will be coming in December. If you have any questions at all about this, or just general JavaScript questions, please send me an email. I'm Josh at pubnub.com, and I'm on Twitter as Josh Marinacci. Thank you. Back to you, Chris. Can't hear you. I think you might still be on mute.
Like that. Hello?
I can hear you now.
Hey, good. So that's the end of the content that we've got. So we're now open to questions.
Awesome. Thank you very much, guys. And that was a very nice little demo at the end there as well. We do have a question straight away, actually. Let me grab that. And if anyone does have any questions, please do throw them straight into IRC, and we can ask Chris directly. So first question. Hang on. Here we go. First question. And the question is from MPA Stephen. And he asks, sorry, it's scrolling slow. There we go. Do you believe that WebAssembly would eventually replace the use of JavaScript and instead use Java in its place on the front end?
Well, that's interesting. I mean, if you take WebAssembly to where it could go, it may not just be Java. I mean, you could use any programming language you like in the browser. I think one of the limitations is down to the quality of the UI and disabling an incumbent that's actually very good at what it does. So it's, kind of persuading people to stop doing JavaScript when it's very good at what it does and start doing another language. Now, it could be Java, but frankly, we've been through several iterations of different Java UIs, right? We've been through AWT and SWT and Java 2D and Java FX, and none of them have managed to survive. So I would be surprised if Java does manage to become a UI language in the future, because it's not been successful at it so far.
Okay, a couple of other questions here. One from Fabrizio. Have you considered the use of GraphQL to coordinate the call to different REST services and the shape of the data?
So things like graph databases, that's kind of a heavyweight solution for what should be a fairly simple task. I mean, where JavaScript and Node.js excels is becoming completely IO bound, where it's really doing very little other than receiving a request, going to various different services to get the response, and then sending it back as a package. That the more time it spends actually waiting for responses asynchronously on other backends, the better and the faster it works. So yeah, if we're talking graph databases, I think that would probably be a heavyweight solution for what most people want to do.
Okay. Any questions from the Java forum? The sound of silence, no questions. Okay, so what we're going to do, I've got a couple of other questions here. What do you think about join Node.js with Java queries, or Java queues, sorry?
Joining Node.js with Java queues.
What do you think about join Node.js with Java queues is the question.
Yeah, I'm not sure I understand the question, I'm afraid.
Perhaps maybe using Node.js to push messages to Java queues, or?
Well, certainly one of the things I find is quite strange, and I don't know if this answers the question, is that we're kind of using JSON REST as the standard language for microservices, so talking between one language and the other. And And yet we're pushing towards, asynchronous frameworks. So reactive is really popular. Node.js itself runs async non-blocking I/O everywhere, but JSON REST is a blocking API call. You make your request and you wait for the response. So I think probably the next evolution around this stuff is going to be having async messaging between different tiers. So I think being able to use MQTT or more likely AMQP as a message queue between Node and Java or between any microservices is going to be a common thing to occur in the future. But I'm not sure if that answers the question.
We'll see. One other question from Destiny Awaits, who's been with us for quite a long time now in the VJEF24, so well done. Just asking if the demo code is going to be available. Is it in GitHub or any links you can share?
Yes, the code is in GitHub. I need to do a little cleanup, and I'm working on a full blog to explain it. So okay. Just follow me on Twitter or send me an email if you want early access.
Okay, perfect. And if you actually, once that's done, if you send that to us, we can share that out on Twitter as well.
Great.
Okay, so we're about 5 minutes to now. So thank you very much. Thank you very much to both Chris and Joshua.